Have you ever really stopped to think about the math of a clock face? How 13 o'clock is just 1 o'clock? Well, it turns out that this super simple, looping kind of arithmetic is actually the bedrock of modern digital security. We're talking about the stuff that protects everything from your bank account to state secrets. So let's unwind this connection and see how a simple clock really holds the key to modern cryptography.
It sounds a little strange, right? What could a clock possibly have in common with billion-dollar cybersecurity? But the answer, you'll see, unfolds this really beautiful and surprisingly ancient story about the hunt for a perfect mathematical system. A system strong enough to build our entire digital world on top of.
All right, so let's start our journey in a whole new kind of mathematical world. I want you to forget the infinite number line you learned about in school. In this world, everything is finite. Everything wraps around, just like the numbers on a clock.
Now, the official name for this is modular arithmetic. And that modulus thing is just the fancy word for the number we wrap around at. So for a 12-hour clock, our modulus is 12. Simple. For the systems we're going to look at, it could be any number really, like 3 or 8, or even a ridiculously massive prime number.
And in this system, numbers that we think of as completely different can actually become the same. So let's say we use a modulus of 3. In this little world, the number 7 is basically the same as 1, because if you divide 7 by 3, you get a remainder of 1. And guess what? The same goes for -8. It's also the same as 1. They're what we call congruent.
So what happens is, all the infinite integers out there get squeezed down into this small, finite set of remainders. We call it Zn. If our modulus n is, say, 8, then every single number in the universe becomes one of these guys. 0, 1, 2, 3, 4, 5, 6, or 7. It's this neat, tidy, and enclosed little system. Or is it?
Turns out, this neat little system has a pretty big flaw hiding in plain sight. A critical weakness, actually, that makes it totally useless for serious cryptography. And it all comes down to this idea of an inverse, how you undo something.
And this table right here shows the problem perfectly. Let's look at that Z8 system again with the numbers 0 through 7. Check out the additive inverse row. It's completely full. For any number, we can find another one to add to it to get back to 0. But now, look at the multiplicative inverse row. It's like Swiss cheese. It's full of holes. There's just no integer you can multiply 2 or 4 or 6 by to get back to 1. It's impossible.
So this is the heart of the problem, this asymmetry. Undoing addition? No problem, we can always do that. But undoing multiplication? Only sometimes. And in the world of security, sometimes is just another word for never. It's not good enough.
So why is this such a big deal for cryptography? Well, think about it. Encryption is basically a multiplication operation, and decryption, that's the inverse. If you can't guarantee you can always find a multiplicative inverse, then you can't guarantee you can decrypt your message. Your entire system is broken before you even start. So how on earth do we fix this? Well, the answer, incredibly, comes to us from ancient Greece. The key to our modern digital security was actually forged over 2,000 years ago by the father of geometry himself, Euclid.
Euclid gave us this tool of just profound elegance, an algorithm for finding what's called the greatest common divisor, or GCD, of two numbers. And it's this ancient tool that's going to help us figure out and ultimately fix our broken system.
So here it is, the fundamental rule. The reason numbers like 2, 4, and 6 had no inverse back in our Z8 world is because their greatest common divisor, with the modulus, 8, was bigger than 1. An inverse only, and I mean only, exists if the number and the modulus are relatively prime.
And here's Euclid's algorithm in action. It's just a beautiful, simple, recursive process. Watch what happens. To find the GCD of two numbers, you just replace the bigger one with the remainder you get when you divide them. You just keep doing that, and again, and you see the numbers get smaller and smaller until one of them hits 0. The other number that's left, that's your answer. It's just such an elegant way to tame these huge numbers and boil them down to a single, simple solution.
And this brings us right to the core of our whole quest. We know we need the GCD to be 1 to get that inverse we so desperately need. But how can we build a system where this isn't just some happy accident, but an absolute guarantee for every single non-zero number?
Well, the answer lies in one of the most fundamental ideas in all of math, prime numbers. They are the key. They're what's going to let us forge those missing inverses and create a perfect, unbreakable system.
It's really that simple. If we choose our modulus n to be a prime number, think about it.
What's the greatest common divisor between that prime in any smaller number? It's always 1, by definition. A prime number doesn't share any factors with smaller numbers, except for good old number 1.
And this gives us exactly what we were looking for, a prime finite field. You'll also hear it called ZP or a Galois field. In this special system, that fatal flaw we found is just gone. Every single non-zero element now has a multiplicative inverse. We can always undo multiplication. We can always decrypt. We've fixed it.
Okay, this is amazing. We've designed a perfect system, at least in theory. But there's one final step. I mean, knowing an inverse exists is one thing. How do we actually calculate it, especially when we start dealing with gigantic prime numbers?
For this, we need a souped-up version of our ancient tool, the extended Euclid's algorithm. It runs the exact same GCD process, but as it works its way backward, it cleverly keeps track of some extra numbers, these coefficients that link everything back to the original numbers. And when it finishes, and that GCD is 1, boom! One of those coefficients it was tracking is the multiplicative inverse we were looking for.
And this is where that 2,000-year-old theory becomes a real, practical, modern tool. This is an actual implementation in the Python programming language. Now, you don't need to understand every single line, but just appreciate how that ancient idea is translated into just a few simple steps of code. Code that can take two absolutely massive numbers and, almost instantly, calculate the inverse, the exact key you need for decryption.
So let's just sum up this whole journey. We started with a simple system, we found a flaw, and then we used Euclid's algorithm to figure out what was wrong. Then we used prime numbers to design a perfect system. And finally, we used the extended Euclid's algorithm to actually forge the tool we needed. So the simple algorithm tells you if a key exists, but the extended one, that one actually builds it for you.
And it really leaves you with this thought, doesn't it? The algorithm that's probably running on your computer right now to secure your data is fundamentally the same one described by a Greek mathematician 2 millennia ago. It's just a powerful reminder that the abstract, maybe even useless ideas of today could very well become the invisible essential foundation of tomorrow.